So first of all, again, we take the time to change this into a form that we can do. We can see that it's going to be a product rule, and then the function on the right has a chain rule, a little chain rule, but it is a minus x on the inside, so it has a derivative on the inside as well. And so when we go, keep one the same, derivative of the other one. And again, it doesn't matter which order you do that in because you're adding them. Keep the other one the same, and then the derivative. And the derivative of the inside will be a -1. Again, what we want to show is that we have a 2 root x on the bottom. I'll just write this as dy dx because this had a dy dx, so to keep a nice format going. I want to have a 1 over 2x on the bottom, 1 over 2 root x. Maybe you remember that that's the same as half x to the negative a half. So it makes sense for me, since I see the x to the half in here a couple times, to factor out a 1/2 x to the negative a half. Put some big square brackets here so we can see what's left. In the first one, we're going to just be left with 3 minus x squared. In the second one, first of all, this whole expression is going to be negative, so I know there'd be a subtract sign here. Taking an x to the half out of the x will leave me with an x. Taking a half out of the 2 will leave me with a 4. So I'll have a 4x, and then I still have the 3 minus x. So at this point, I would have that 2 root x on the bottom with what I factored out. I'm just going to rewrite the top because this is where coming around, seeing different things, I'm going to show you 2 algebraically different ways that we could go from here to help you solve this for the show that. I'll show you my favorite way first, and then probably a more typical way that people would do it. For this one, for my favorite way, since I know that my answer wants a 3 minus x, and I look at what I have right now, that I have a 3 minus x in both terms, I can factor it out as a common factor. If I do that, I would be left with a 3 minus x from the first term minus a 4x from the second term. And then just simplifying that second one, we're done. Okay? Often what's more typical, and I'll do this one all in green, often what's more typical, what people will do is when they get a couple things on the top, they feel like, well, if I expand this, what's the worst I'm going to have is a couple x squareds, then I'll probably be able to factor. So it won't be too bad. And you might miss seeing that you could factor out that 3 minus x. And if you do expand it, you're going to get 9 minus 6x plus x squared minus 12x plus 4x squared over 2 root x. And combining your like terms, you get 5x squared minus 18x plus 9. And then you say, I can factor this, and factoring to get a 5x squared would have to be a 5x and an x. any ways to get 9 is either 3 and 3 or 9 and 1. If we look at 3 and 3, my outside is 15, my inside numbers make 3. If they're both negatives, then you will get negative 18x. However, this doesn't quite match what we want to show that to be. Because instead of 3 minus x, we have x minus 3. Instead of 3 minus 5x, we've got 5x minus 3. And so you could just factor out a negative, and it would look, if I take a negative 1 out of the first one, I'll get 3 minus 5x. If I take a negative 1 out of the second one, I would get 3 minus x. And of course, negative 1 times negative 1 is just positive 1 anyways, so that would give me 3 minus 5x, 3 minus x, all over 2 root x. So maybe you can see why I like the first method better, but doing this isn't wrong, and it shows some nice things about, this concept of factoring out a negative 1. That idea comes up over and over again. They taught it to you in, here, let's do some mental math. I'll show you where you were taught it in grade 12. We'll go x minus 15 minus x. I'm going to pick a value for x, and I want you to evaluate this. X is 375.24. Go. Close. Negative 1. Good. Why? Because if you do factor a negative out of one of these, you get another x minus 15, which simplifies just to be negative 1. Doesn't matter that I picked 375.24. I think that's what I picked. So that idea of factoring out a negative is important. It comes up in different places. So I liked seeing this technique that some of you did, because it helped remind us of that as well. So now that we've shown that what we wanted to show, the second part of this question said, find the x-coordinates of all the points on this function where the tangent is horizontal. And we're going to look at this with GeoGebra as well, because it's some cool things that are happening, and having a graphical approach is nice. So now that we've got our derivative, what do we know about tangents and horizontal? So we want a flat line. First of all, the tangent, well, that's connected to the derivative, because the derivative is the slope of all the tangents. Okay? And if we have a horizontal tangent, what do we know about the slope of that tangent at that point? It'll be 0, because it would be completely flat, right? So the slope would be 0. So we go down to our equation. We go down to our equation and we say, well, now I know my slope would have to be 0. And this whole process of simplifying it was nice because, well, first of all, if a fraction is equal to 0, the only way a fraction can equal 0 is if the numerator is 0. So we really don't even have to worry about the 2 root x on the bottom at all. And since the top is already factored, you can go directly to the answer. Top will equal 0 either when x is equal to 3, because that would make the first one 0, and 0 times anything would still be 0, or when x is equal to 3/5, because that would make the second one 0. And those are the 2 points where it's equal to 0. So I'm going to load this up on GeoGebra. Okay, so there we have our function. And can you see that right there? Oh, wait for it. Close enough? Pretty much horizontal. And then down here again, it's horizontal. We found one of our places where it was horizontal was when x is 3. The other one where x was 3 divided by 5, about 0.6. Oh, I'm so close. And there is our graph of our derivative. Now what's going to be, this question is alluding to something that we're going to do in our next part, in the applications part. Things are very important at maximums and minimums. Okay? This is the key application of calculus to business, to different things, because you often want to find maximums and you want to find minimums. You want to find maximums of what would be the maximum volume I could make using a certain amount of material. If your material is limited, then you want to make the biggest rectangular box possible to hold the most stuff. That'll be advantageous. Okay? You might want to find minimums in economics, minimum cost to doing something. So if you have a graph that shows what's happening in different situations, you can use calculus to find those maximum and minimums and then be able to make economic decisions, business decisions based on that. All right, so we'll take some time to work on these questions. And again, look at the back and try to match them up so you practice your algebra skills.